Here's the second video for chapter 8, and we start drawing Lewis structures. What these are diagrams that show where the electrons are in a molecule, which atoms are sharing, and how many electrons are being shared. So we end up placing bonds. They can be a single, a double, or a triple bond. Single bond has 2 electrons, or you can say 1 bond. So every bond is made up of 2 electrons. And it looks like that with the CC there, with just a single bond right there. A double bond is just double that. So 2 bonds, it looks like this, and that is made up of 4 electrons. So we'll want to get used to the fact that each dash here is representing 2 electrons. And then a triple bond is 3 bonds, like it sounds like, and that's 2, 4, 6 electrons being shared. The single bond is the longest and weakest bond. It's kind of like one single long stick. It's really easy to break. Whereas if you take 3 short sticks, like this triple bond, it's very strong. And it's a shorter bond. So the reason atoms are forming bonds in the first place is because of what's called the octet and the duet rules. So an octet rule is saying that atoms will gain, lose, or share electrons in order to have 8 valence electrons. So they want to be like a noble gas. Noble gases have 8 valence electrons. The duet rule is kind of the exception to the octet rule. So everybody's going for 8 except for hydrogen and helium. They will only have 2 valence electrons, primarily hydrogen, because once again, helium's not going to bond a ton. So we really have to remember that hydrogen only wants 2 electrons. And if that's the case, that means he only wants 1 bond. So hydrogen can only have 1 bond, and then he is done. So here's our rule for writing Lewis structures. First, we have to add up the valence electrons for the atoms in a molecule. And I'm realizing I don't think we've mentioned this yet. Oh yeah, we did. Valence electrons, if you go back to last chapter, we talked about how the valence electrons, you can find them from electron configuration, but the quick rule here is if you look at the periodic table, group 1, the alkali metals will always have 1 valence electron. Group 2 will always have 2 valence electrons. You hop over to boron, group 3, they will always have 3 valence electrons. Group 4, which is carbon, they will always have 4 valence electrons. And then you keep moving on over. Nitrogen's group, group 5, has 5 valence. Oxygen's group has 6 valence. Fluorine's group has 7 valence. And then the noble gases have 8. So their group numbers are equal to their valence electrons. We'll keep practicing that as we go. I'm going to play these rules out as we go, okay? So if we just look at CH4 here, to draw its Lewis structure, what we're going to do is first add up the valence electrons. So carbon is in group 4, so he has 4 valence electrons. There's only 1 carbon, so there you go. Hydrogen is in group 1. He only has 1 valence electron. And there are 4 of these hydrogens, so each one has 1 valence. There's 4 of them, so that gives me 4. My total valence electrons to work with here are 8. So once I find the total, I don't care who brought which ones to the table. I'm just going to try to make everybody happy with those 8. So what it tells you to do is put the least electronegative element in the middle that isn't hydrogen. Hydrogen can never be in the middle because what did we say? Hydrogen only wants 1 bond. So automatically carbon has to go in the center here. And then you surround that center atom with all the rest, which is 4 hydrogens in this case. Okay, and you connect the outer atoms using single bonds. So single bond, single, single, single. At this moment, I have used 8 electrons, 2, 4, 6, 8 electrons. That was my total. So I pause and see if everybody's happy. Carbon wants 8 electrons around it, and it has 8 electrons around it. So that's good. Hydrogen only wants 2 electrons, meaning 1 bond, and each of these hydrogens only has 1 bond. So that's a perfect Lewis structure, and we're done. Okay? If we look over here at PCl3, so we add up our valence again. Phosphorus is in group 5, so he has 5 valence electrons. Chlorine is in group 7, so he has 7 valence electrons. There's 3 chlorines, so 7 times 3 gives me 21. We add it up and we get a total of 26. So here's our order of doing this. Remember, we put the least electronegative element in the middle. It's also the one who's generally by himself. So you see how there's PCl3? P is furthest from fluorine, so he is the least electronegative. He's also single, so he goes in the middle. I put chlorine on any 3 sides. You can go on any side, it doesn't matter. And remember our order, okay? We next fill these with single bonds. So what I did next was single bond, and single bond. At the moment, I've put 6 electrons, right? I've got 26 to work with. Once you do the single bonds, you go to the outer atoms next. So I'm going to go give chlorine a total of 8. He already has 2 that he's sharing with P. So then I'm going to put 4, 6, and 8. This chlorine already has 2. So I add 2, 2, 4, 6, 8. And this third chlorine, he already has 2. And then 4, 6, 8. So I pause again. I've taken care of all the outer atoms, right? I stop and count. There's 8 here, 8 here, and 8 here. That gives me 24. I have 26 to work with. So if I've filled up the outers and I have extra, I then go to the center atom, which is P, and I put those extra 2 electrons there. So at this point, I've hit the 26 electrons. I'm out, and I check and see if everybody's happy. Well, phosphorus has 8 around him, and each chlorine has 8 around them. So everybody has hit the octet. I've used the correct number of electrons, and I'm done. Just to show you a couple ways you can draw this, you can write 2 dots every time, or you can also put these dashes like this, okay? Those each represent 2 electrons. Let's look at a couple other scenarios. I've put these 2 stars here, which seem to be helpful sometimes. Here's kind of 2 additional rules. If you have extra electrons after you do the outer atoms, you're going to add them to the center atom. So if you have extra, they go in the center. However, if you run out of electrons and everybody is not happy, that's when you're going to have to use a double or a triple bond. So you don't do a double or triple unless you are out of electrons and you need help filling everybody up, okay? Let's look at those examples. There's HCN right here, so we add up the valence electrons. Hydrogen is in group 1, he has 1 valence. Carbon is in group 4, he has 4 valence. Nitrogen is in group 5, he has 5 valence electrons. We add those up and we get a total of 10. Here we do HCN, C's in the middle because he's the least electronegative, who's not hydrogen. We start with single bonds, right? So a single and a single. Then I take care of the outer electrons, or the outer atoms. Remember, hydrogen is already done because he can only have 2 electrons. So I go focus on nitrogen. He had 2, so I went ahead and put 4, 6, 8. So I now have taken care of the outer ones. So I pause and count. 2, 4, 6, 8, 10. I've put a total of 10 electrons here, which is all I have. But if you look around, hydrogen is good with the duet. Nitrogen's good with an octet, but carbon only has 4 electrons right now. Carbon needs to get 8, just like everybody else, right? So this is the scenario where if you run out of electrons before everybody's good, you're going to have to make a double or triple bond, which means you're going to share more electrons. Hydrogen can't make a double or triple bond, so don't worry about him. But what nitrogen can do is be nice and donate his lone pairs. These are called lone pairs if they're out here not being shared. Lone pairs can be turned into a bond. So I'll take 2 here and put them in, and I'll take 2 from the top and put them in. And let's count now and see what I just did. Have we still used a total of 10? 2, 4, 6, 8, 10. Yep, we still have a total of 10. And then you see if everybody's happy. H has 2, carbon has 8, and nitrogen has 8. So this is the correct structure. Everybody's happy. We had to use a triple bond because we ran out of electrons. Here with BrO3 minus, we run into one more thing here. Similar rules, we still go with valence electrons first. So bromine is going to be 7 electrons because he's in group 7. Oxygen, each one has 6 valence electrons, times 3 gives me 18. And then here you see this -1. So this is actually a polyatomic ion bromate. If you have a -1, ask yourself, how does something become negative? Well, it must gain electrons, right? If it's a -1, that means he has gained 1 additional electron. So I have to add that in to the valence electrons. Whereas if it was a positive, I would actually have to take away that electron from the total. So here I've got 7 and 18, and I'm going to add an additional 1, so I get a total of 26. Then I use my normal rules. Bromine's going in the middle, oxygen on the outside, and I do a single, single, single. take care of the outer atoms first, all of the O's. And then you always want to pause and count. So once I've filled up the O's, I'm going to have 8, 8, and 8, which is 24. I have 2 extras so they can go on the center atom. And at that point, everybody has 8. I'm also out of electrons, so that's perfect. And what I have here, you can't see it super well, but if you have an ion, you want to put brackets and show that charge out here. So that says -1 up there. There are some exceptions to the octet rule. We've already talked about hydrogen being one of those, because hydrogen only wants a total of 2 electrons and then he's done. But we also can have more than 8, and some atoms want less than 8. We'll talk about it. So the first one here is one that we will not cover. If you come up with an odd number of electrons, you have done something wrong. So we will not talk about molecules with odd number of electrons. They do exist, but they're real unstable. They react very quickly. We won't talk about them. There are some that want less than an octet, and there's only a few of them. Boron, aluminum, and gallium. If you look on the periodic table for these 3, they are all right there together in group 3, which helps you remember them a little better. They actually prefer only 3 bonds. I will explain this a little bit later why. But they only want 3 bonds, which means if you are not forced to give them more, then you don't. Of course, if there's 4 atoms around them, you have no choice. But if you have the option, you want to just give them 3 bonds. So here I would do my same rules where boron has 3 valence initially because he's in group 3. Fluorine has 7 valence. There's 3 of him, so that gives 21. We add it up and we've got 24 to work with. Okay, so we do boron, fluorine, 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 single, 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 fill up the fluorines, and pause and count. Well, at this moment, we've used 24 electrons. The fluorines are happy. Typically, the center atom would be short, right? And what we would need to do is share another set of electrons right here to make a double bond. But what we know is boron actually is happy with just 3 bonds. He's very stable like that, so we're going to leave him as is. An expansion of an octet is when you have more than 8 valence electrons. In order to do this, there's 2 things you have to have. What I mean by that is for an atom to have an expanded octet, more than 8 valence electrons around it, it has to be the center atom first off. So it has to be in the center of the molecule. It also has to be on the 3rd row of the periodic table or below. So phosphorus, sulfur, chlorine, or below. Any of those can have an expanded octet or more than 8 valence electrons. For example, PCl5. You follow the same rules. Phosphorus has 5 valence, chlorine has 7 valence, multiply by 5 and you get 35. We have a total of 40 to work with. We put P in the center and put the 5 chlorines around. And when we do single bonds for each one, and then we fill up the outer atoms and we pause and count. This moment, we are up to 40 electrons. All of the chlorines have 8 valence, which remember, the outer atoms have to only have 8. But the center P has 2, 4, 6, 8, 10, which would strike you as odd, except that you know that P is the center atom. He is in row 3 and below. Like if he was nitrogen, this could not happen because nitrogen's up here on the periodic table. But P is allowed to have an expanded octet. So he has 10 valence electrons and he's happy with that. Here is PO4 minus 3. This gives us a little bit of an idea of why this happens. So you could draw a correct Lewis structure that looks like this. PO4 minus 3 here. You could also draw another correct Lewis structure for PO4 minus 3. Here, phosphorus only has 8 valence electrons, but here he has 10. What we're going to see is that phosphorus is actually more stable when he has 10 valence electrons. That's based on this thing called formal charge, which I'll get into in the next video.